In this video, we're going to do some geometry the way the ancient Greeks used to do it, using compass and straight edge construction. We're going to take a look at a couple different constructions. 1, an equilateral triangle. 2, bisecting a line. 3, drawing a parallel line to a given line. Inscribing a regular hexagon in a circle. Inscribing a regular pentagon in a circle. Cutting a line into 3 or more equal parts. Bisecting an angle, and making a tiled floor in perspective. Okay, let's get started. So obviously you're going to need a compass and straight edge if you want to follow along at home. You can get a nice little kit like this that has your compass, boom, and then it has some extra leads and a place to store a pencil underneath, and the box itself is a straight edge. And so this is great for if you're working in like a notebook like this. Great for doing little practice drawings and stuff. But for what we're going to do today for these demonstrations, we need something a little bit bigger. So I'm going to get rid of these. And this is the compass that we're going to be using right here. I found this in my garage. It is old and rusty. It's missing the little thumb screw that tightens it down, but it is so rusty and tight that it's not going to go anywhere once we set it. So we're going to be able to draw some nice big circles with this and be very, very precise with the settings on it. Also have this metal straight edge here. It has cork on the back so that I can just sort of set it against the desk and it will stay. The numbering on here, that is not traditional in the compass and straight edge construction. So that we're going to have to ignore the fact that we can measure with this. That wasn't part of the way the ancient Greeks used to do it, but that's just a little adjustment that we have to make. So the rules for the straight edge are as follows. We can connect any 2 points with a line. Okay, we can extend the line to any arbitrary length we need. So that's really all we can do with the straight edge. Now with the compass, we can do a couple things as well. We can compare lengths. So we can set the compass to the length of this line here, and then we could check that against another line, or we can set this to the radius of a circle and then choose a point for the center of our circle, and we can draw a circle. We can also just draw a little portion of a circle. So, like that. Now there'll be a lot of times where we don't need to draw the entire circle. We're just going to use the intersection of this circle and this circle to generate a new constructed point. So constructed points are any points where a circle and a line meet, or 2 circles meet, or 2 lines meet. Those are points that are generated or constructed by the diagram that we're building. So now let's use some of these rules into an actual construction. So this here is going to be Euclid's construction from the elements of an equilateral triangle given a particular side length. So first we set our compass to the size of that line, and then we pick a point on one end of the line. We set our compass, we draw a circle. Okay, and then we're going to set the compass at the other end of the line, and we're going to draw another circle. If we can get it to stay. There we go. All right, so now we have 2 circles that are intersecting at a point there. And the distance from there to there, from there to there, and from there to there is all the same. They're all the radius of this circle. And so now we can use our straight edge. I'm going to do this in red. There we go. An equilateral triangle given a specific side length. Okay, so in addition to using this diagram to draw a triangle, you can use the same construction to bisect your original line by connecting these 2 points here. I'm going to use black, like that, and this is a perpendicular line at the midpoint of that line. So this construction works for all of those things. And then we can construct another parallel line on here in the following way. Set our compass to be the length of that line, and we're just going to do the same basic construction. So the two purple lines are parallel. And so you can see by just applying those basic rules, we can start to build up some pretty complicated concepts just from these, few simple starting points. So let's go on and do some more complicated things. Okay, for this construction, we're going to inscribe a hexagon inside of a circle. So the first thing we're going to need is a circle. And now, what we're going to do is we're going to pick an arbitrary point on our circle here. So I'm going to go connect the midpoint here and just use that. Just draw a little line there. And that's going to just be the starting point for us measuring out our hexagon. So we're still set to the same radius of the circle. We just want to start at a point on the circle, and then we're going to start marking off the vertices for our hexagon. And so you'll notice I'm not drawing full circles. I'm just drawing a little piece of the arc that intersects with the circle. This will keep things from getting too sloppy and messy. As you can see from the earlier diagram, very quickly it becomes pretty complicated. All right, and that should sort of wrap back around to our original point. Indeed it does. And now we're just going to use our straight edge to connect all of the points. And I think I'll use the red again. All right, and there we go. Hexagon inscribed inside of a circle. So now we're going to inscribe a pentagon inside of a circle. This is going to be much more difficult. I'm just going to draw a line through the diameter there with the straight edge. And then we're going to bisect that line. All right. Now we want to bisect this line here. draw a smaller circle. Okay, and now we should be able to just start connecting up some of these points in order to construct our pentagon. Okay, and there you go. There is a regular pentagon inscribed in a circle. So it turns out that there are only certain objects that you can inscribe in a circle in this way, and it follows a very specific formula. It's known as the Gauss-Wantzel theorem, named for Carl Friedrich Gauss and Pierre Wantzel. A regular n-gon can be constructed with a compass and straightedge if and only if n is a power of 2, or the product of a power of 2 and any number of distinct Fermat primes. A Fermat prime is a prime number of the form 2 to the 2 to the k plus 1. For k equals 0, this is 3. For k equals 1, this is 5. For k equals 2, this is 17. For k equals 3, this is 257. For k equals 4, this is 65,537. So these are the 5 known Fermat primes. So since there are 31 combinations of anywhere from 1 to 5 of these Fermat primes, there are 31 known constructible polygons with an odd number of sides. So for example, we can construct n-gons with 3, 4, 5, 6, 8, or 10 sides, but not with 7 or 9 sides. But there's other things we can do besides constructing polygons. So earlier I showed you how to cut a line in half. That's called bisecting a line. What if we wanted to cut this line segment into a bunch of equal parts, any number of equal parts that we wanted, 3, 4, 5, whatever we wanted. Turns out that there is a systematic way we can do that with a compass and straightedge. So what we'll need to do is we're going to draw another line that's about the same size, maybe a little bit longer than our first line. And we just want it to meet here at one point so that we have this nice angle here at the vertex. And then what we'll do is we'll take our compass. So we'll do 3 parts in this one just to make it easy to see, but so we'll want to set it to about 1/3. Enough. That's about right there. And then we'll just go ahead and make some little marks here. Alright, so I think we'll want to extend that line just a little bit because we want it to be about even. It doesn't need to be exact. But remember, we're allowed to extend a line segment with the straightedge. That's a little bit better. All right, so from there, what we're going to do is we're going to actually set our compass. So from there, what we're going to do is we're going to set our compass to be the same length as from there to there. And then we'll draw an arc with that radius, and then we're going to set it to the length of this line that we drew, like that. And then we're going to position this here. We're going to find the intersection point there. Awesome. All right, and then next, we are going to use our straightedge, connect these 2 points. that. Then we're going to take this length here, and we're going to transfer those down to this new line. Great. And then we just are going to connect these up with the straight edge. And we should have 3 equal parts on our original line. And now if we take our compass, we should be able to confirm by 1, 2, and 3. So those 3 segments are all of equal length. So now we can do that with lines. Can we do that with angles? And it turns out we can bisect an angle, but we can't necessarily trisect all angles. So let's take a look at the bisecting of an angle. We'll just do it on the same page here. Start by drawing some arbitrary angle. And then we'll go to work with the compass. We want to set that to sort of a comfortable length, somewhere around there. We're going to just get 2 intersection points there and there. And then we're going to take the length of this point. And we'll do it again from here. And we want to get their intersection just right there. And then we just take our straight edge and we go through that point and draw our line segment. Actually, I'll use red for this one. All right, and so now we have split that angle in half. That is called bisecting an angle. Unfortunately, there is no general way to trisect all angles. There are some that you can do it for. There are some you definitely cannot, like a 60-degree angle or a 20-degree angle. Those, it is not possible to trisect, meaning to split into 3 equal parts using compass and straight edge. So there are 3 classic problems from ancient Greece that turns out compass and straight edge simply cannot solve. Now, it's possible to solve these in other methods, but not using the rules of compass and straight edge. Those are trisecting an angle, which in 1837, Pierre Wantzel proved that is not possible in the general case, because you can be forced to have to construct a length that is the root of a cubic polynomial. In addition, there's another problem that Wantzel proved is not possible to solve with compass and straight edge, and that is doubling the cube. Say you have a cube that is 1 by 1 by 1, and you want to double it so that its volume is now 2 rather than 1. This then requires a side length of the cube root of 2, and Wantzel proved that this is not constructible by compass and straight edge. The third problem is called squaring the circle, and the idea there is, say you have a circle of a certain area. Through compass and straight edge alone, can you turn that into a square of the same area? In 1882, this was proved to be not possible as a consequence of the Lindemann-Weierstrass theorem, which showed that pi is a transcendental number and therefore is not constructible by compass and straight edge. Okay, so up to this point we've done constructions with both a compass and straight edge. But are there any constructions that we can do with just a straight edge? Well, here's an example of doing a tiled floor in perspective. So first we're going to need a horizon line. And then what we want to do is we want to essentially draw 2 lines coming off here that are slightly different lengths. And then we will draw in our first tile. Okay, and then we need to draw a couple of guidelines. So I'm going to use the red for that. So we're just going to draw this line here. So we can connect sort of the nose point, that vertex, and then this new constructed point here. And go to the horizon on that. And then we're going to draw a second line from that horizon point to the edge. From that horizon point to that vertex there. Okay, so those are the only two construction lines that we need, and then from here on, we're going to start building out the various tiles. So we just want to connect the corner there to this new construction point here. We just keep going. We can do one more. As you get down to the end, the sizing just gets very difficult to deal with here. So I think this is the last one we'll probably be able to do. And have it look like anything at least. Okay, I think that's the last one we'll do for this drawing. You can see as you get sort of farther back, we're now getting to the point where the thickness of the pencil is starting to become an issue with being able to see the tiles. But as you can see, we now sort of have a tiled floor that is receding into the distance, and each of our tiles are tapered. They are becoming foreshortened. They're shrinking and getting smaller as we would expect them to in sort of proper perspective. And so this is a sort of a good little introduction to some basic perspective. Here we have a horizon line and vanishing point. This is technically a two vanishing point perspective because our tiles are both sort of tapering to these 2 points. These two lines, again, were just guidelines. So as you can see, we can do, some basic perspective on a two-dimensional surface here. We've got sort of this three-dimensional look just from using our straight edge. And so that'll do it for this video. I hope you enjoyed doing a little bit of geometry the way the ancient Greeks did it, using compass and straight edge constructions. Okay, and that'll do it for this video. Hope you enjoyed it. Thanks for watching.